Right, materials assessment 2, definition of density, mass per unit volume. Part B, you are asked to work out the combined mass to make the rod of brass of volume 0.8 times 10 to the minus 3. So brass is made out of copper and zinc. 70% of the volume is copper, 30% is zinc. So you could work out the volume of each by doing 70% of this volume and 30% of this volume. So the mass of the copper, it's the density of copper multiplied by the volume of copper, which was 70% of this volume here, and that gives us 5 kilograms. The mass of zinc is the density of zinc multiplied by the volume occupied by zinc, which is 30% of the total volume, and that gives us 1.7 kilograms. So the total mass of brass, the alloy, is 5 plus 1.7, which is 6.7 kilograms. So the density of brass, that's the overall density of the entire material. It's the mass, total mass divided by the total volume. We've just worked out the total mass is 6.7. We know that the volume occupied by both zinc and copper are 0.8 times 10 to the minus 3 meters cubed. So we get a density of 8.4 times 10 to the minus 3 kilograms per meter cubed. This question, a lot of students mess this up because there's a lot of information given, and you have to be sure of which information you are using. Okay, so in this question, they give you a couple of extensions. They also give you a cross-sectional area, a stress when it obeys Hooke's law up to that point, and then they give you this additional piece of information here at the end that throws a lot of students. This is only specific to the maximum load, so the breaking point. Okay, so do not use this data if you are not considering the maximum stress or the breaking position of that material. Okay, so here it says calculate the Young's modulus. That's stress over strain. The stress, the values we are going to use is the values up to where Hooke's law is obeyed. So we know that this stress qualifies for that. And the strain, we can use this information here. So we know that the extension is 52 millimeters, and that's times 10 to the minus 3. Remember, you have to convert it into meters. And divided by, this is the extension. Remember, strain is extension over the original length. So the strain that we work out is 0.026. The stress is 1.8 times 10 to the 8. Divide the stress by the strain, and we get 6.92 times 10 to the 9 pascals. Okay, the following question, it's breaking stress that we need to calculate. Okay, so this, we need to know the point, the force that is required, and what's the cross-sectional area. So we've been told that the force required to break material is 45. The cross-sectional area, it says that this sample has a constant circular cross-sectional area, but they give you diameter. So here I have to use pi r squared. This is the diameter divided by 2. I've put the diameter, remember it was 0.55 millimeters. I need to change that into meters. Divide by 2, get into radius in meters, square it, times it by pi, and then do 45 divided by that, and I end up with 2.3 times 10 to the 8 pascals. Breaking strain, again, this is the strain associated to the breaking point. So what is the extension of the material just before it breaks? Well, they give you that there. That's to just before it breaks is 88 millimeters. Put into meters and then divided by the original length, and that is the breaking strain. So I can write it in this as well. This I'm using, I'm writing it like that. This is what we're going to use later on. So I've come back and written this in because it's I'm going to come use in just a moment's time. Also, this I've written out the strain in a unit of times 10 to the minus 3. So this is where I'm going to use it. It says sketch a graph of axes below showing how you expect the tensile stress to vary with strain. Mark a value of stress corresponding and the corresponding strain at the limit of Hooke's law and the breaking point. Because there's a grid, you are expected to put scale on the axes. Okay, so do we know the stress that Hooke's law is obeyed to? Yes. Well, if you read the question again, it says Hooke's law is obeyed up to a point where stress is 1.8 times 10 to the 8. So I have split the scale up from 0 to 2.5, and I put times 10 to the 8 embedded on the axes. Strain, remember, doesn't have any unit, and I've used times 10 to the minus 3 based on the numbers that I've got. Now, what's the strain when hooked up to the point of Hooke's law is obeyed? Well, we work that out here. Okay, so we used a stress where up to where Hooke's law was obeyed, and we knew it was 52 millimeters for when that was happening. So we worked out the strain there, and I've put the value here, and that's 26 times 10 to the minus 3. So that's somewhere 26 times 10 to the minus 3, somewhere in between 20 and 30. And that is a stress of 1.8 times 10 to the minus 3. Now, remember, this is strain and this is stress. We can still plot a Hooke's law line on stress and strain because this is force over a constant of area, and this is strain, which is extension of a length. So there's a straight line we can draw up to that point, and we know that the breaking stress is 2.3 times 10 to the 8 pascals, and we know the breaking strain is 0.044 or 44 times 10 to the minus 3. So that's 44 times 10 to the minus 3, and there is 2.3 times 10 to the 8 pascals. So those are the 2 points I've plotted, and I know Hooke's law is obeyed up to this point, and I know this is the breaking point. That's where I've ended my line. And if this is where the point Hooke's law is obeyed, then beyond it, Hooke's law is not. So that's why I've curved it off here. Okay.